as Shuping said, a lot of the work I do is in catalysis, and we've really benefited a lot from all of the amazing work that's gone on in the materials project in terms of developing data sets and workflows and tools. And most of the things that we do in catalysis right now start with a material science question on what is synthesizable or what is stable, and so on. And I'm going to try and highlight how that fits into what we do, why there are some things in catalysis that make the problem quite a bit more complicated, and how I see machine learning and these general data sets sort of fitting in to make some of these challenges more possible. So before I jump in, of course, I need to thank the awesome group of student researchers who have actually done all the work. This was done, this picture was from just after the lockdown was lifted in Pittsburgh, but before we returned to a mask mandate at CMU. But it's been really fun. You can see Pittsburgh in the background. This is a park that's right next to CMU campus. At Carnegie Mellon, we have a ton of excitement about machine learning and material science and chemistry and chemical engineering. Besides myself, I think something like 70% of the faculty in engineering self-associate with doing machine learning and engineering right now. And so if you have interest in any of these areas, or you ever want to come and visit Pittsburgh, feel free to shoot me an email and I'll try my best to make it happen. Okay, so my group works in a lot of different application areas. There's a lot of exciting challenges in catalysis right now. One example that I'm going to talk about in a little more detail is taking CO2 and turning it into fuels using renewable electricity. This is an area that has gotten more and more interest, especially with things like the recent IPCC report highlighting just how challenging it's going to be to address climate change in the next couple of decades. This is a really, really hard catalysis problem because there's both activity and selectivity challenges. We also work on water splitting chemistries, trying to evolve oxygen and hydrogen for hydrogen fuel cell energies. A lot of the more traditional thermal catalysis, taking small molecule building blocks and turning it into something more valuable, is not electrochemical, but is thermal in nature. And so there's a lot of really interesting questions about how to do very selective chemistry with a specific C2 product or make one thing over another. This is really challenging and really core to making things like plastics or high value added chemicals. We do a little bit of work with water quality remediation. I'll highlight that in a couple of slides. And then there are a couple of areas that we work in, like designing polymers for catalyst interfaces that are a little bit closer to the material science realm, but still rely on the same sort of interfacial catalysis and surface science studies that I'll be talking about. There's also a lot of excitement at Carnegie Mellon in general on trying to develop new methods for additive manufacturing. We have this awesome ARM Institute and the Next Manufacturing Institute, and a lot of the challenges that they face there are fundamentally surface challenges as well. If you're trying to reduce surface oxidation or build coatings for high temperature engine parts, a lot of those are basically the same science problems that I'll be talking about for surface catalysis. So just to give you a feel for maybe more specifically what one of these questions might look like and why material science is so important, I just wanted to highlight this project with Mike Janik and Rob Ryu and Zachary Liu at Penn State University. This is a DOE funded project that we work on together. And we're interested in binary alloys and binary intermetallics. And the difference between the alloy and the intermetallic is the alloy is a disordered solid solution. This is probably the most common form of catalyst that we might use in industrial processes, some sort of solid solution of a binary. But as you all know, as the experts in material science, for specific compositions and for specific binary combinations, instead of forming a solid solution, you form an ordered intermetallic. And this is really interesting as a surface scientist, because when it comes time to form a surface through one of these materials, if I form it out of an alloy, I'm going to get sort of a random distribution of possible active sites for catalysis. But if I form it out of a very, very strongly ordered intermetallic, I can find composition regions where we go from maybe isolated active atoms, let's see if these are isolated palladium atoms. And if I change the composition just a little bit from about 15% palladium in a zinc lattice to about 19%, the atom that gets substituted forms a trimer on the surface. And this is really, really interesting because if you're trying to react to C2 on the surface, you can go from a material that doesn't want to interact with this acetylene molecule to one that wants to interact with a C2 intermediate much more strongly. And you get very, very large changes in activity and selectivity. And in answering a question like this, the very first thing we have to do is go to the material scientist and say, okay, first of all, if I have a binary that I'm interested in, like palladium zinc, what is the phase diagram? Can you predict that ahead of time? What are the structures that are going to be there? What are the other metastable things that we need to draw from? And these are all things that the materials project and others have done such an amazing job of making it easy for people like myself to draw on. As another example, I wanted to highlight some work that we're doing with Anubhav Jain, who also is part of the materials project, obviously, and Wei Tong at LBL. And we've been lucky to work with some graduate students as part of the materials project, Ryan Kingsbury and Christine's group, Duo Wong and Anubhav's group, and Richard Tran, who also happened to do his PhD with Xu Ping, and has contributed a lot to PyMyGen and materials project type applications in the past. And in this project, we're interested in trying to design new catalysts for nitrate reduction. You have excess nitrate in some water quality stream that you're trying to reduce out. And we want to take that nitrate and turn it into nitrogen or ammonia or something that's a little bit easier to separate. And this is a very complicated process. There's not that many catalysts that are well known. The ones that we do know of are very expensive, like palladium or platinum. And so we've been working with Anubhav and the others to basically screen things from the materials project and find interesting alloys or intermetallics that might be better for this chemistry. And I'm not going to go into details of this, but if you have questions, I'm happy to answer them afterwards and or share the data and or discuss exactly how we're doing it. I think in some of the other applications, you'll sort of see the tools that we use in order to solve a problem like this. Okay, so when it comes time to understand what's happening on one of these catalyst surfaces, this is sort of an overview figure from Karsten Reuter's group, who's a world expert in developing microkinetic models at the Fritz Haber Institute now. The way that this usually looks is we start with some assumption about some simple properties that we think might be interesting. We use those to screen possible binary combinations or ternaries or some other material space for catalysts that might be interesting. Once we have a certain surface or set of surfaces that we think are interesting, we drill down and we start thinking about what are the particular active sites that might be responsible for the activity on a structure like this. We model all of the elementary processes, individual elementary steps for all the reactions that can happen. If we still think it's interesting, we might go to a more complicated microkinetic model, perhaps that has diffusion or some sort of surface lattice. There's a ton of catalysis that considers simultaneously adsorption, desorption equilibrium, along with diffusion, along with reactions on the surface. These all go into a larger microkinetic model that allow us to predict activity and selectivity. And then once we have this microkinetic model, we can analyze it with things like sensitivity or rate determining step analysis to try and figure out what are the right descriptors or what are the rate limiting steps. And with that information, we go back to the beginning, develop new descriptors, screen again, and continue this process in a loop. And this workflow is relatively straightforward, right? It's been successfully applied in a lot of different applications of catalysis over the past 20 or 30 years or so. But it is very expensive and there's a lot of complexity. And so a lot of the work that we're doing now is trying to develop things like machine learning models to make this process faster or easier, so that we can expand the sort of space that we search when it comes time to try and optimize something. Okay, why is this so difficult in catalysis? So even for a really simple chemistry, like I want to take syngas, which is a combination of carbon monoxide and hydrogen gas, and I want to mix those together and I want to form something with value. This is also called Fischer-Tropsch, or there's a number of other hydrocarbon related reactions that you could think of here. If I take CO and hydrogen, the best case scenario is a catalyst that makes one thing that's valuable and doesn't make anything else and doesn't burn it to something like CO2 and water. And so if I introduce the syngas mixture to specific rhodium surfaces, this is really interesting because it will form selectively acetaldehyde among many other possibilities like methanol, water, methane, ethanol, and other possible outcomes. And even for this relatively simple reaction network where we're just starting with CO and hydrogen, and we just are going up to a few C2 products, you can already see that there's something like 150 or 200 different reaction intermediates that we can consider here. There are a ton of different reactions that can happen to connect these different intermediates. And identifying exactly what is the right path through this reaction network that happens on a specific rhodium surface takes an overwhelming amount of computation. It's really, really, really complex. And this is a relatively simple chemistry. So this is what makes our lives so difficult and why it's been a little bit complicated to extend all the cool things that have happened in the material science world strictly to catalysis. Okay, so most of our screening approaches look something like this. We're interested in stable materials. We usually start with the materials project and then add data from additional databases like AFlow or the phases database at Penn State as needed. We take those stable materials. We then screen on things like, is the material stable under a specific set of electrochemical reaction conditions? There's been a lot of awesome work in Ulissi Gen in making the Porbet analysis for this robust and stable and really, really, really fast. We've really benefited from all the work that's gone in there. Usually when we down select here, we're left with often order 10,000 to 50,000 different specific structures that we think might be stable. This part is relatively well defined. There are awesome workflows to do these first two steps. And then the next sequence, we want to find the stable surfaces. This is easy for a monometallic. Can get quite complicated if you have an intermetallic or binary or ternary. There's a lot of surfaces. And also it's a little bit difficult to find the right terminations. At this stage, we often have order millions of possible surfaces that we're trying to consider. When it comes time to start placing adsorbates, there are a lot of different adsorbate workflows. Most of them don't work amazing yet. It's not very mature. There's a lot of work in this area right now. After we think of all the different ways we can place an adsorbate on the surface, we often have order millions or tens of millions or hundreds of millions of possibilities that we might want to screen in order to understand activity across a very wide material space. If we want to take into account things like surface coverage on the surface or different reactions, this number really, really easily gets up into the order of billions. And these calculations, billions of calculations, are sort of what would be required if we really wanted to understand activity and selectivity across any arbitrary catalyst surface. And this is scary to me as someone who does calculations, because order 50,000 DFT calculations I can do, right? I can go to your favorite DOE or NSF supercomputer facility, write an allocation, go ahead and build a little workflow and do this. Order 1 million, I'll show you an example where we did this. Order 1 million is starting to get very expensive, but it still sort of limits the feasibility. Once you get to hundreds of millions of billions, it's basically infeasible to do this with brute force DFT. And so right from the beginning, looking at a workflow like this, we sort of know that either we have to be very careful about the materials that we consider, or we need something like machine learning to make this process faster and allow us to learn from things that we've done in the past. Okay, so let me show you an example of one of the things that might go into this order 100 million sort of space. So this is an example of an OH adsorbate sitting on a ternary surface. We see there's three different types of atoms: little green, big purple, and this OH. It's a relatively straightforward calculation. We guessed that it was sitting sort of on top of the green. We did a number of steps with our favorite electronic structure code, and we saw that the OH moved a little bit going from the green to the purple. And even this super simple local relaxation often takes something like 1 day or 2 days on a really fast computer at something like DOE NERSC, the Cori supercomputer. Okay, this is like the simplest thing that we can consider. I showed you a reaction network that had C1 and C2 intermediates. Something that's a little bit more representative is something like this, where there's 2 carbons, 2 oxygens, a bunch of hydrogens attached. This is one of many possible oxygenate species that I could consider for a C2. It's not even doing anything very interesting. It moves over a little bit. We see one of these OH groups sort of rotate around and it shifts. The entire surface goes up and down a little bit as it tries to settle down. And because of the additional degrees of freedom here and the fact that there's more atoms, this calculation often takes 4 or 5 days on a fast computer. And just think about all the different ways I can take this adsorbate, rotate it around, try different sites on the surface, right? The number of degrees of freedom is really, really, really large here. So this is why it's quite complicated. Okay, so I know that this is a super broad audience. So what I'm going to do is I'm going to give a super high level overview of how we might use machine learning methods to screen space for something like CO2 reduction. And then I'm going to get progressively more detailed in talking about the data sets that we've been developing and new machine learning models in order to make this whole process faster. In this first story, I'm going to completely gloss over all of the machine learning because this was work that was done 3 years ago. And already in the past 3 years, the machine learning models that we were using back then are completely out of date compared to the stuff I'm going to show you afterwards. So I'm just going to give you an idea of how we fit this stuff together, and then we'll start talking more about what the state of the art is. One of the points I want to get across as I do this is that the things that are happening in the catalysis community right now, in terms of large data sets and complex models, I think are going to have a lot of benefits for the material science community as well. There's no reason that the things that we develop in catalysis can't also help materials at the same time. So hopefully some of these later things, some of you find applications for outside of the ones that we were considering. Okay. So for this introduction example, I want to talk about that first application that I mentioned at the very beginning, taking CO2 and turning it into something more interesting. This is the simplest possible pathway I can think of for a stepped copper surface. I have CO2, I bring it down onto the surface, I add a hydrogen, I add another hydrogen, and a water pops off. I add another hydrogen, and another, and another, and eventually a methane leaves. And there's finally an oxygen, and then that eventually leaves as water as well. This is just CO2 to methane. There's other competing pathways. This is a super oversimplified picture. But what's really interesting about this is when you do these sort of microkinetic models, you can sort of identify the steps that are most challenging. And in this specific pathway, the step that is most complicated, most difficult to happen on the copper surface is taking the CO molecule and adding this first hydrogen. The CO to CHO step is generally considered to be the rate limiting step on a copper surface. You can do explicit nudged elastic band calculations to try and find the transition state between these two. When you do that, what you find is that the transition state looks a lot like a partial desorption of the CO molecule. And so a descriptor that's very helpful for CO2 reduction is what is the binding energy of the CO molecule sitting on a surface. I'm going to come back to that in a second. We're not the first people to think about CO2 reduction on various catalyst surfaces. So there was a lot of amazing work by Hori and others over the past several decades, basically brute forcing the problem, making cathodes out of every possible metal that you can think of from the periodic table. And what the community has found is that if you make your cathode out of iron, cobalt, nickel, palladium, platinum, or any of these other materials, you generally bubble off a bunch of hydrogen. Cool if you want hydrogen for a fuel cell, bad if you want to turn CO2 into something more interesting. If you make your electrode out of zinc, gallium, silver, gold, you make CO. Also cool if you have a combination of CO and hydrogen, that's syngas. And I just told you that syngas can be selectively turned into other things. So that's also interesting, but it's not taking CO2 and making something really valuable. There are things that are more valuable than carbon monoxide. If I make it out of tin or cadmium or indium or these others, you get a bunch of formate. That's sort of because the CO2 binds 2 oxygens down. And that's a very interesting behavior. But what's really cool is that there's only one metal that's known to make C1 and C2 products, and that's copper. That's the one I just showed you. That's why we start with mechanisms on copper to understand why is it so special and what's going on. Using this really, really simplified descriptor of the CO binding energy, we can rationalize why copper is special. So on the x-axis is the CO binding energy, the free energy of CO. On the y-axis is the partial current of methane or a C2 hydrocarbon. So we want this to be higher. And what we see is that on the right-hand side here, if your CO binding energy is too weak, you make CO, it leaves the surface, and you bubble off a bunch of CO. All of these points are the ones I just showed you, silver and gold and the others, that make a bunch of carbon monoxide. They bind CO too weakly to keep it around and do something cool. Everything on the left-hand side are things like palladium and platinum and other materials that bind CO so strongly that they sort of poison the surface, and then the only thing that's left is for them to evolve hydrogen. And so we can sort of rationalize what's going on with copper by saying, well, It's the only one that appears to have an intermediate binding energy of CO, where you're strong enough that you keep it around, but weak enough that you can do something cool with it and it doesn't just poison the surface. The natural question is to say, look, why is there this huge gap between all of these things on the left-hand side and the right-hand side? Why is copper sitting there? And what if we could find other materials that are like copper sitting near the top of the volcano? Again, a very simplified picture, but a very interesting material science question. This is what I asked the first PhD student in my group to do, Kevin Tran. He's now working at Schrodinger on material science workflows there. And basically, he went to the materials project. He said, please tell me all the stable materials made out of all these elements in gray. He took those. He automated the calculations that we needed to do for the surface chemistry. We built an active learning workflow with some machine learning models. Basically, what was going on was we had an automated workflow. We would collect everything in databases. Every night at NERSC, we would kick on a couple of very simple machine learning models to build the best models for CO and hydrogen absorption energies that we could. We would take those, we would try and solve a design of computational experiments problem over the course of the next day. What are the additional calculations that I should be doing to help my machine learning models or find the next material? And then those would get scheduled and automatically distributed, and this process would repeat every day. This was something that was quite difficult 4 years ago, but has progressed a lot since then. And I think even in PyMyGen now, this has gotten quite straightforward. Christine and others have really cool workflows now to basically do similar things for CO and hydrogen for things like photocatalytic CO2 reduction, which is really exciting. So even in the past few years, we've seen a lot of maturity in this area. Okay, we applied the workflow. We found a lot of materials that were interesting. About half of the materials in this sort of window were copper containing. About half of them had no copper whatsoever. That was quite exciting. There were more things than we could actually verify with DFT. And what we did was we were talking to experimental collaborators at the University of Toronto, and we said, look, we have all these materials that we think are interesting, various compositions, and quite a few of them we've done DFT calculations, and they say they should have a really interesting CO and hydrogen binding energy. So why don't we go ahead and test some of these things experimentally? The ones that we focused on initially were binary combinations where it seemed like no matter what we added, it would help the process. So on this map, this is a T-SNE map. We want things in this deep purple region. And so things like copper aluminum, no matter how I add aluminum to this copper, it seems like it helps to weaken the CO binding energy a little bit. And that's supposed to have a good impact on CO2 reduction. So this is best case scenario for talking to an experimental collaborator. It's, look, copper aluminum is interesting. No matter what you do, it might be even more active. So that was at the top of the list. Quite a few of these other binary combinations, copper gallium, copper tin, aluminum nickel, also looked quite interesting. All of these ones in purple were the ones that we highlighted as potentially exciting and worth following up on. Our collaborator, Ted Sargent at the University of Toronto, spent a lot of time digging through and trying to verify these. Anyone who's done electrochemical experiments knows that it's not just enough to know the right composition. There's a ton of engineering that has to go into making it high surface area, tuning the structure, really making sure you understand the synthesis conditions and so on. Once we identified this copper aluminum material, his students took the extra time to really optimize this material and really dig into what the limitations were. This was particularly exciting because copper aluminum was not only found to be quite active for CO2 reduction, that's great. It was also found to be quite selective for ethylene out of all the possible C2 products. So at a specific current density of about 600 milliamps per square centimeter, it was making almost 80%, 75 or 80% Faraday efficiency ethylene. And ethylene is one of the most valuable building blocks that I could think of to make from CO2. So this was super exciting. To be 100% honest, we got lucky here because nothing in the workflow I showed you allows us to predict selectivity to ethylene. That's something that we're working on now. That's something that is going to be, that is coming based on the models that I'm showing you. But we were able to say certain binary combinations were more likely to be active than others. And so we were sort of doing a very coarse down select. Okay, so this work came out in Nature last year. We're following up on other materials right now. But again, really the challenge in my mind in Catalysis is not just activity, but selectivity to multiple components. That's really complicated and something that I don't think anyone is really good at right now. Okay, so I want to switch gears a little bit and start focusing in a little bit more on the machine learning methods that we're using in the data sets that we're building. The first thing that we do is my group spends a lot of time thinking about how to build active learning workflows and simple machine learning potentials to accelerate individual calculations. If you're running a relaxation, if you're optimizing your favorite structure, you don't need to do every step with DFT. You can skip steps with a machine learning potential. You can use information from prior potentials. There's a lot of different schemes for doing this. Online active learning is the simplest one. Basically, whenever you have a machine learning potential and it's uncertain, you stop and run a calculation. If the machine learning potential is good, you continue. There's other interesting design of experiment strategies you can use, like offline active learning. We develop a lot of code and methods here. I'm not going to go into details, but if you're interested, please look at the repos or send me an email, and I'm happy to share. The calculations that we do on the Catalysis side are so expensive that we want to play all the games that we can to reduce the number of DFT calculations to the very, very bare minimum. To give you an idea of what's currently possible, it seems to be relatively easy to reduce the number of calls by about a factor of 2, which is good but not incredible. And I think there's stuff coming that should make it even better than that, especially when you're sharing calculations among multiple relaxations. Okay, this is sort of a small data sort of mindset. This is, I'm just running a single calculation. Can I make this thing run faster than I would be able to otherwise? The other way that we could go is we could say, what are the more complicated representations that we could build? And what are the machine learning models that could benefit from even more data than just the current calculation that we're running? And anyone who's been working in this area, I think we all sort of realize now that this field is moving extremely quickly. Month to month, the models change. There's a huge number of different machine learning representations that we could use. How we represent these atoms to the machine learning models is by far the hardest part of this process. We can use things like composition, like Auto Map Miner, I think is one of the best examples of that for building automatic features. We can use fragment-based methods. We can use natural language processing. We can use local environment descriptors, graphs, molecular orbitals, 3D convolutions, inverse Fourier representations of the lattice. All of these are things that material scientists and chemists and physicists have come up with the ways of representing it. And if you look at the time scale on this, a lot of these representations have only been around for the past few years or have only been popular for the past few years. So this is really, really exciting. It's also very early days. We don't really know exactly what's going to win or what's going to work the best, but there's a lot of possibilities. Okay. At the end of the day, what we're really looking for is a very general potential energy surface in Catalysis. And what I want to be able to do is I want to be able to relax a structure like this and do a local minimization. I want to be able to do global minimizations, tell me the best configuration on a surface, maybe with a multi-start method or something else more complicated. We spend a lot of time doing transition state calculations, finding paths through these little landscapes. And if we're interested in dynamics, maybe we're doing some sort of molecular dynamics or something else to basically figure out how materials will sample from the surface. All of these different uses in Catalysis would all benefit from a very, very general potential energy surface that worked for a adsorbate like this on a binary or ternary surface like this figure that I'm showing you. So I'm going to go back to this example, right? This is the one that I showed you in the beginning. And the question is basically, what would it take to build a universal potential energy surface that would work for any small molecule on any inorganic surface? This potential energy surface doesn't exist yet. I'm going to show you the work that we're doing in this area. If we had such a potential energy surface that was fast, this would make our lives much easier, and it would really expand the scope of questions that we could be asking. Okay, these are things that we are developing in collaboration with Facebook AI Research. Specifically, Larry Zitnik is a research scientist there. And this Open Catalyst project that I'm going to be talking about is the work of a lot of different people on both the FAIR and the CMU side, as well as people at NERSC. Brandon Wood also did a lot of work with the Materials Project. He worked with Christine as a PhD student, others at Stanford. This has gotten to be quite large, but I'm really, really excited about the sort of things that we've been doing and the progress that we've been making in this area. Okay, so what are we trying to do in the Open Catalyst project? The most important thing that I want to get across is, as chemists and physicists and material scientists, a lot of us have the math backgrounds to learn machine learning methods. Awesome. We can build new potentials and play around with things. That's great. But a much faster way of doing things is to work closely with the machine learning community and turn these things into competitions that really get everyone excited and everyone developing new models at the same time. And so one of the things I've been most excited about is basically working with Larry, who's done this for a lot of other challenges in the past, to basically make this as accessible as possible to a computer scientist. Along the way, we're also trying to answer some questions like, in Catalysis, how big of a data set do we need? Thanks to the Materials Project and AFlow and others, we know that hundreds of thousands of inorganic materials is enough to build a really, really good model to predict electronic properties or formation energies. That's awesome. In Catalysis, if I want to do any adsorbate on any surface, I really don't know how much data I need. I could believe hundreds of thousands, I could believe millions, I could believe billions, right? And that's going to inform how we go about this process. Okay, so the first thing that we did was we worked very closely with the people at FAIR to develop this Open Catalyst 2020 OC20 dataset. It is a dataset where we took a lot of stable structures from the Materials Project, metals, intermetallics, built materials, ionic compounds, 2D materials, randomly cut them into different surfaces, randomly placed adsorbates that have applications to fuel cells, agriculture, ammonia, CO2 utilization, hydrogen, and so on. For every one of those, we did a little relaxation, we did a little bit of off-path sampling, we ran some short time scale MD, we did a little bit of electronic structure analysis. A lot of this benefited from the tools in PyMedGen and ASC and other cool codes out there. And in total, we ran over 1 million of these relaxations, each of which was full ab initio DFT. That resulted in more than 150 million individual single points with DFT. And in total, it was something like 70 million node hours. That's not core hours. That's not nurse service units. That's node hours, right? This was a huge ask. But our hope is that this data set is helpful for a lot of different projects and helps us make more general force fields and helps the rest of the community on the call today. Okay, this is an example from the data set. This is actually the same one that I showed you before. This is something that lives in the OC20 data set. I'm not going to go into details on the sampling procedure, but I'm happy to discuss in detail afterwards. Relatively standard Catalysis workflows, basically place things on a surface, do a relaxation, reference the energies, and deposit them in a very, very simple database. It's extremely sparse. There's less than one calculation per adsorbate surface pairing. This is not the data set that I want to solve all the Catalysis problems. This is the data set that I wish I had had 5 years ago to build really general machine learning models that would work across really wide swaths of material space. We spent a lot of time talking about different tasks that we could explain to the computer science community and say, look, this is exactly what we want you to solve. So there's black box DFT. I think for the people here, this is the most general and the most likely to help what you're doing. This is just a general surrogate model for density functional theory or some other ab initio code. We also want people to help us predict the relaxed states directly. And in Catalysis, usually we just care about the relaxed energy. And so if we could just, given the initial structure, guess the relaxed energy, that would also be very valuable. We have a leaderboard system. Different people can submit automatically. And these tasks are obviously interrelated. If you solve this very, very general S2EF task, you can also solve the other two. So there's a lot of different strategies here. I don't care what methods you use to win, but we're open to creative solutions to this challenge. Okay. Because the point of this was to encourage machine learning research, we didn't just dump all the data. We dumped it as specific train test splits. This is really important if you want to make sure that things are apples to apples afterwards. We have a test set that we didn't release. When you submit to the leaderboard, we evaluate on the test set that you don't know. And then we use that information to say, how well does your model actually work on something that has never been trained on? This is really important if you want to get the computer science community interested. We built a lot of models. Some of these were standard last year, CGCNN, SNET, DimeNet++. In the past year, we've developed a couple of new ones like ForceNet and SpinConv. I don't want to spend a ton of time going into the details of these models because it's a little bit, there's a lot of notation and there's a lot of complexity in how these things are built right now. But I just want to sort of highlight what these models look like and give you some idea of the challenges. And if you're interested or you think these things are helpful, shoot me an email and we can have a discussion afterwards. Okay, as an example for DimeNet++, this was the baseline model as of last year. As a material scientist, I don't expect you to get anything out of this diagram besides the models are really complex. There's a lot of free parameters. There's a lot of things that are being fitted. State-of-the-art models now have more than 1 million degrees of freedom in optimizing various parameters inside of here. This is huge. And because these models are so large and the data sets have gotten so big, training one of these state-of-the-art models now takes order 300 to 1,000 GPU days. So it's not like I have my little gaming computer under my desktop. I'm just going to go ahead and train a machine learning model and use it for what I'm doing. We really entered the realm of really, really large data sets and really deep models. And so this is becoming more and more of an issue. And I'll talk a little bit about how we're scaling these things. Okay, I'm not going to go into detail on the SpinConv model besides saying this is the new state of the art. We released this in June. Already in the past 6 months, we've seen a lot of progress. As I said, as these models get larger and larger, every time we make the model larger, it seems like the accuracy gets better. This is in contrast to other small data problems where you tend to overfit if you make the model too complex. With this really, really big data set, it seems like the larger we go, the more interesting this gets. This is work that Brandon is really leading as one of the NESAP postdocs, along with Steve Farrell and others at NERSC. We're looking at scaling these models to the upcoming Perlmutter computer right now to say, what is the limit? If 8 million parameters is better than 1 million, why don't we try 10 million or 100 million or a billion, right? Like has happened in the natural language processing realm. Again, I don't expect you all to understand all the details here, but just to give you a sense of where this field is going, this is new to me. 3 years ago, we were developing very small models and training was a lot easier, but this has become more complicated. Okay, so on the top row, one of these is density functional theory relaxation that I showed you before. One of these is a relaxation that was done with SpinConv that has seen this sort of adsorbate in the past. I don't know about you, but I can't tell the difference in the final structure. It's not always this good. This is a little cherry picked, but this is the first example I've seen that says that we can really develop a general machine learning potential for this sort of system. The bottom one I think is even cooler. The model has never seen the CHO adsorbate. This is one of the ones that I implicated in the copper CO2 reduction pathway, but it's being asked to do a relaxation on a binary surface. One of these is SpinConv, one of these is DFT. Again, it's never seen CHO before. Visually, I can't tell the difference, right? This is really, really, really exciting to me. This is the first data that I've seen that says maybe there's hope in developing this sort of machine learning potential. Maybe we don't need individual things for every individual surface that we're going to develop in the future. Okay, I don't want to go into details here, but basically I just want to say this is cherry picked. It doesn't always work this well. We have not solved the problem. The number that I want to highlight is when it comes time to predict an energy, it's only very, very close to DFT, about 10% of the time or less. So as a material scientist, I want this number to be like 99% or 95%. So we still have a long ways to go. We haven't solved it yet, but even in the past 6 months, this 10% has gone up from 4%. So I hope that it will continue to improve in the future. All of this is public. There's a website, opencatalyst.org. There's a leaderboard. You can see what's happened in the past 6 months. We have progress from ourselves, Texas A&M, DeepMind. Others have already submitted. DeepMind was just last month. People are being really creative. So AJ Medford of Georgia Tech came up with this multipole expansion method. This was the group from Texas A&M that had this spherical message passing system. Both of these are new architectures that were developed for this very complicated data set. DeepMinds took a different approach. They were basically adding noise and using super, super deep GNNs with a huge number of layers. Also very interesting, very creative. And again, what's most exciting to me is this is the sort of progress that we've seen in the past 6 months. I expect similar things to happen in the future. In addition to this general leaderboard, we also have this thing called the Open Catalyst Challenge as part of the NeurIPS conference coming up in December. If you're interested in this, there's a specific challenge that we're trying to solve here. The deadline for this is October. The top couple of people who submit against this challenge will be chosen for a talk at NeurIPS. And so we're hoping to really coalesce a lot of this activity and get everyone excited. You can see a rough timeline here. If you're interested in the details, there's also a link on the Open Catalyst Project website with this challenge data set. Okay, so I think I'm pretty much out of time, and I want to leave plenty of time for questions. So I'm going to skip this bit on uncertainty. And I just want to end with a little summary of all the things that we use. So I tried to highlight all the places that we use PyMatGen and Fireworks and Atomate and ASE along the way. But really, every single thing I showed you starts with some combination of PyMatGen and ASE and other stuff built on top. The code that we use for making calculations faster is on our group repo, AmpTorch and ALMLP. This ALMLP is active learning for machine learning potentials. Feel free to check it out. It's all public. If you have suggestions or anything doesn't work, let us know. We're happy to fix things or work together or whatever. The graph neural network potentials I showed you are very general. This repository is very, very powerful. A lot of software engineering has gone into making these models fast and scalable and extensible. They scale to hundreds or thousands of GPUs now. That's very exciting. If you're interested, check out what's in here. It's not really limited to Catalysis. We've used exactly the same repository for predicting things like bulk materials properties, surface energies, transition metal complex energies, right? A lot of this is very general. Most of the adsorbate placement work that I showed relied on this CatKit code from Suncat. And then we've also done some work on uncertainty estimation in these structured property relationships. I skipped over that, but there's 2 repositories, one on benchmarks and one for calibrating uncertainty estimates that I also find really helpful day to day. So I just wanted to highlight. Okay, so if you're interested in any of the Open Catalyst project stuff, feel free to shoot me an email or Larry, or ask questions on the discussion board or on the GitHub repo. We've been really excited by the interest that we've gotten so far, and a lot of the questions that we've gotten have really helped us clarify exactly where we needed to improve. So with that, thanks again. Thanks again to all the students and all the funding sources, and I'm happy to take any questions you have.
Thank you, Zach, for the great talk. And we are now open for questions. So I think there are already at least more than 10 questions, 16 questions. So Zach, why don't you take those questions that you would like to take, and yeah, on the Q&A.
Yep, excellent. Yeah, I'll go through them one by one. All of these look really interesting. So let me, the first one is, have you considered using Optimade? Because I was showing examples like this. Let me go back a little further. I said we start with querying a bunch of materials databases in order to figure out what's interesting. We've played around with Optimade a little bit, and I went to the Optimade workshop this year. I'm really excited about that. I don't have anyone who has a lot of expertise, and I do have a lot of people in my group who have a lot of experience querying from the materials project. So just out of laziness, we've been continuing to do that. But I think it's exactly the right thing to be doing, so that you submit one query and you get it from all the different databases. So I think that API has also come a long ways in both the API and the implementation on each of the databases. And so my impression is it was still a little rough last year, but this year it's working pretty well for a lot of examples. So hopefully we'll do more of that in the future. Chi Chen asked, how do we know which path in the reaction network is the right one? So for example, here, how do we know that a CO doesn't move sites in this process, right? I've just represented this as a single adsorbate location. This is a great question. It's the sort of thing that comes up when you start doing very detailed lattice models of a surface. It's relatively easy to do one of these lattice models for a pure metal surface. It gets more and more complex when you go to a binary surface where you can have the surface diffusion. Usually we assume that just the lowest energy one is representative, and that usually works as long as there's a very large energy difference between the different sites. But if there's a small energy difference, then yes, that can be a limitation. What I think is going to be really interesting is over the next 5 years, now that we have more general models, I think we're going to be able to incorporate multiple active sites into these models more easily. Whereas in the past, we could only screen on just CO energy overall. I think we can start to do the sort of things you're talking about. But when it comes to a binary surface, there's just so many active sites that you have to do something to sort of simplify the process. Otherwise, you just get bogged down in complexity. In catalysis, we're also often very lucky in that things tend to be linearly correlated. And so I think our field gets by with more simplifications than sometimes seems reasonable, simply out of luck that so many of these adsorbates are very similar and interact in the same way. It allows us to sort of get at trends without having full realism and full fidelity across every single one of these surfaces. But it doesn't have to be that way. We're a little bit lucky and unlucky in catalysis. Okay. Abhishek asked, each of these molecules has some sort of preference for different sites on various surfaces. How is that automated? So how do we know exactly what's happening there? So this is one of the things I wanted to highlight. There's not amazing workflows when there's more degrees of freedom for finding all the different ways something can sit on the surface. So there's some awesome code by Joey Montoya, who's now at TRI, who was working with Christine, who I think put one of the first sort of general adsorbate placement methods out there and sits in PyMatGen, and we've used that quite a bit. That's really cool. It has some issues with additional degrees of freedom, like rotational degrees of freedom or more complex adsorbates. That's why we've been using this CatKit code. Jeff Greeley from Purdue has also worked on some similar methods. At the end of the day, none of those are really up to all of the degrees of freedom and complexity into saying what are all the different ways to consider on a surface. But I don't think there's a fundamental reason why that has to be the case. I feel like the new graph-based methods work fairly well. It's just a matter of getting the latest code or getting the community to all agree on one current standard set of methods and get it into a place like PyMatGen or ASE or somewhere else that everyone can see and use. So I think it's coming. Those methods just haven't been around for very long, and so it's just a matter of consolidating, I think, at this point. Okay. Sorry. So on slide 15, the question is, I mentioned ML-based models. In this case, they were not interatomic potentials. So what was going on was I would show it a site like CO sitting on top of a nickel, and I would ask the model to directly just tell me the energy. This is the energy is what I care about. That's the GCO I was showing before. The more general thing is build a machine learning potential and actually do a relaxation and say what is the best site on a surface. But when we did this work 4 years ago, it was impossible to build a machine learning potential that worked for CO across any arbitrary metal surface. Just nothing existed, right? The closest thing I think was Xu-Ping's magnet model, which was really cool and sort of had this sort of idea of a graph-based model that could interpolate and had some idea of angles and bonds and degrees of freedom and so on. But even with a model like that, we didn't have the data set to really train. And so we started with the simple thing, given the structure, just predict the energy. This is also the IS2RE task that I showed later on. But now that we have really, really interesting models, we're using more and more interatomic potentials now to solve that sort of challenge. But again, that's why I didn't want to go into details here, because the stuff we were doing 4 years ago is already out of date. Okay. Another question was, when it comes time to build a machine learning model, like for example, maybe maybe one of these, can you predict some other property besides just energy and forces? Short answer, yes, no problem. We can predict energy here. We can predict forces as a gradient of the energy. We can do a direct prediction on energy as well. If you're predicting a vector instead of a number, that sort of restricts the type of models you can have. There's a subset of graph methods that are invariant versus equivariant. So if you have a dipole moment, for example, you want your model to be equivariant, and that sort of restricts the sort of models that you can use. If you're just predicting the energy or the stability or the band gap or something like that, you can use an invariant model. So there's a little bit of subtlety there, but there's no fundamental reasons that you can't predict something else. And when you look at the models that have been trained on the materials project data sets, inorganic materials, things like CGCNN or SNET, in addition to formation energy, a lot of those use other things like electronic properties as targets. So that's, I would say, fairly mature at this point. Nothing is stopping you from doing that sort of thing. Okay, another question, how do we check the accuracy of the ML code with some data set far from training set? Right, this is a great question, right? And at the end of the day, as much of the work goes into the test sets and train test splits as anything else. So what we did was we defined 4 different train test splits for this OC20 data set. One is I show you a bunch of adsorbates, and I ask you to predict the energy or forces for the same type of adsorbate on a composition you've seen before. This is in domain. This is the simplest. Can I interpolate among the adsorbates and the materials that I already have? In addition, I can ask the model to train on one set of adsorbates and then predict on a different adsorbate that it's never seen before. So that's actually what was happening here. I trained the model on a bunch of things that weren't CHO, but were hydrocarbons. And then I asked it to predict on CHO. You could say that's very similar to this. You could also say that's quite different. And then the third thing that we did was a binary composition that was quite different, or hadn't been seen. So I show you nickel alloys and I show you gold alloys, but I never show you a nickel gold alloy together. And I ask you to predict what the energy on a nickel gold surface is. That's representative of where we see ourselves in catalysis a lot of the times. All of those things are collected in these data sets that I showed here. Basically, these are all the 4 different train test splits. One of the coolest things that I've seen is that this new spin comp method doing explicit relaxations appears to have roughly flat energy MAE error on the relaxed energy across different train test splits, even when extrapolated. When I saw this data, I didn't believe it. It seems counterintuitive. I don't understand how it's doing just as well for out of domain compositions and adsorbates as in domain. But I think this is the first data that I've seen that says that it's perhaps learning something fundamental and not just memorizing individual data for different adsorbates. But your question is exactly the right one. You really have to be explicit. If you're interested, feel free to shoot me an email and we can discuss in more detail exactly how this was done. Okay, let's see what else. So another question is, in the long term, would it be possible to predict kinetic parameters or transition state energies directly, skipping the PES generation and modeling part? I don't know. So when I think about this transition state problem, it's really complicated to say which transition state do you mean from A to B. If I show you an initial state and a relaxed state, maybe you could guess that there is a particular type of reaction that's going to be interesting. But in catalysis, a lot of times it's not obvious what the individual steps are. You have simultaneous bond breaking and things moving on the surface. And so I'm not quite sure that you could do this direct prediction. what you can do is, given an initial state and a final state and a scaling relation for a type of reaction, you can often guess what the transition state energy is going to be. And there's been a lot of success in that. But I'm not 100% confident that we're going to be able to really nail down exactly what is the transition state energy without actually doing some sort of a potential energy surface. Another important point here is that in catalysis, we use these things called linear scaling relations a lot to simplify our lives. But often the most interesting materials are the ones that don't obey those scaling relations, the ones that are outliers. And so we have to be a little bit careful if we make too many assumptions. There could be a different mechanism for specific types of surfaces that we missed, and those are sometimes the most interesting ones. And so that makes our lives a little complicated. Even if we could guess it 90% of the time, the 10% of the time where we couldn't guess it might be the most interesting ones that we should really drill down on. Okay. I see another question on other descriptors for the CO2 reduction process. We've done most of our screening on CO and hydrogen, and those are the obvious ones. But if I were to predict selectivity for CO2 reduction, I would want descriptors like this for C2 molecules sitting on a surface, like OCCO or other intermediates that have been implicated in carbon-carbon bond formation. We have models that can predict these things. We just haven't applied them to CO2 reduction yet. So I think that's the obvious next step. But this is still very recent. We just haven't had a chance to do it. But that's a great idea. Another question on incorporating the competitive aspect into MapBench. Sure, we're open to it. We've chatted with Anubhav and others about MapBench. That looks super cool. Nothing is stopping that from being part of it. The only thing I think is the data set is quite large. So it's something like a terabyte of data on even compressed. And so that's posed a bit of a challenge. If someone wants to scrape the data and add it to MapBench or add a link, I'm more than happy to include it. At this point, the more people, the better who get excited about this. I think we'll all benefit. So whoever has excitement and the bandwidth to push this forward, we're more than happy to work with you in order to make that public or make it more accessible to other communities. Okay. And Shuping, feel free to stop me whenever you want to cut this off. I'm also happy to keep on answering questions. I have a few.
Yeah, I think there are just a few left. I already helped answer a few of them that are not related to the seminar, but
okay,
yeah.
Sure.
Okay.
Okay. So there's a question on alloy solid solutions. When are they going to do something different for CO2 reduction or HER compared to intermetallics? So that's a great question. Basically, it comes down to whether or not you get very specific behavior for specific ensembles. If you just sort of have an averaged effect, maybe it doesn't matter, and maybe it's very similar. But if your adsorption location really requires two metal active atoms to be right next to each other, and if they're isolated, that might do a different chemistry, this is a specific situation where you might get different behavior. It doesn't happen all the time. In this case, it happens because the adsorbate's a little bit larger, but it does happen sometimes. So there's not one clean answer to that. CO2 reduction is more likely to have something interesting. Hydrogen evolution, the hydrogen is so easy and so simple and so small that it usually doesn't care quite so much. But again, there's not one answer. For the other reaction you mentioned, oxygen evolution, there's other challenges like what is the right coverage and what is the right termination and the right mechanism that make that problem really hard. It's a little bit less about what is the specific active site ensemble on the surface. Okay, so let's see. So an anonymous question is, for the OC20 competition, is there a way to make a separate competition that is restricted to small models that aren't using a ton of computing horsepower? So this is an awesome question and something that we have debated quite a bit. So I would say it's currently early days. I don't know what's possible. I could believe large models are going to win. I could also believe that very small models with a ton of physics are even better. I could believe that someone comes along with something like a type binding method that has all the right physics and doesn't need a million parameters and is somehow fast and is even more accurate than what we've shown. And so we've been a little hesitant to try and narrow things down too much before we sort of know what's possible and what's feasible. But we are very aware that most people don't have 300 GPUs. I don't have 300 GPUs, right, to be clear. That's not something I can do day to day. And so what we have been doing is, and I didn't chat about this, on the leaderboard, you can self-report training time and inference time. So there's hidden fields here that basically say how expensive was it to train. It's hard to do that apples to apples, so it's just self-reported right now. The other thing we've done is in this IS2RE task, there's two different strategies. One is you look at the initial structure and you guess the final energy. The second strategy is you do a relaxation with the potential energy surface, a surrogate, and then you find the final energy off of that. The relaxation with the surrogate is much more data intensive and much more expensive to run an inference. And so I think when it comes time to do the challenge, there's going to be two different sets based on direct predictions or relaxations. And the direct ones are still expensive, but not overwhelmingly expensive. They're not the ones that take hundreds of GPU days. Academic labs can definitely do this. The final thing is in the train test splits, I didn't talk about it, but there's different size train test splits with 10,000, 100,000, 2 million, 20 million in all for each of these. And nothing is stopping you from training on 10,000 or 100,000 and reporting state-of-the-art results. Everything we've seen so far is that the models that do well on 10,000 tend to do better on 100,000 and tend to do better on all. So my guess is that if you can do better on the 10,000, that's going to help the bigger ones as well. It doesn't have to be that way, but most things tend to improve and continue to improve. So I think that's very interesting. We're also very lucky in that we're asking these questions right now while there are all of these new GPU supercomputers coming online. So Oak Ridge, Argonne, LBL, all the NSF computers, most of those have a bunch of GPUs available. So this year and next year, more than any other year, it is going to be possible to ask for the sort of GPU resources that you need to train one of these models. And my experience working with those resources, specifically NERSC and Oak Ridge, is that they are very, very excited to have people building these models. And so I don't think you'd have a ton of overhead in trying to get resources right now to train state-of-the-art models. But 100%, we don't want this to go in the direction of only people with the most resources can win. If we do go that route, we at least need to make sure that those general models can be tuned afterwards for individual applications, some sort of transfer learning or something else, so that not everyone has to repeat the process. Okay. Another question is there a specific advantage of using GNNs versus something else, like a force-based machine learning method or some other descriptor method or something else? Short answer is there's not a reason that graph-based methods have to be the best. The only reason I focused on them so far is that they're the only ones that, as far as I know, have worked across so many different element types. If you ask your model to predict across 45 different elements across the periodic table, it has to be able to learn why copper is different from nickel or vice versa. And the graph-based methods have been able to learn those sort of rules. Most of the descriptor methods have not done as well in extending like that. This Gaussian multipole expansion that AJ came up with is a very clever scheme to get around this. So this is a non-graph-based method that knows why different elements are different. So I expect other models to come along. I really hope other people are creative here. We only did GNNs just because that was those are the only things that seemed to scale at the time. But by all means, try something else. I think there's a lot of opportunities. This GMP model is super cool. It's also implemented in AmpTorch, which I described as one of the repos. Okay. Last couple of questions. So, is there power in incorporating experimental data sets in the literature through mining or through some high throughput effort to augment or improve these models? So if the goal is to predict experimental activity and selectivity, short answer, yes, I think you need experimental data. And if you look around the country or around the world, there are more and more people who are building high throughput automated setups for catalysis and electrochemistry and other setups. That includes LBL, Caltech, University of Toronto, Japan, all over the place. People are excited about these methods, and I think it's going to become easier and easier to try these things. So we're actively working in this area and trying to work with people to see where these things benefit each other. But anyone who has done experimental electrochemistry knows that it is very complex to do those experiments, and they're very detail oriented, and product detection is very difficult. And so it's been a little bit difficult to really get the automated setups to the point where you can compare apples to apples. But 100% that's the direction things are going. And especially I am really, really, really interested in open data sets of experimental properties. There's a really cool one for oxidative coupling of methane that I'm aware of from Japan. But other data sets like that, so that we could compare where these methods work the best, I think would really help the community. If you're aware of others that I've missed, feel free to shoot me an email. But there aren't too many that are really large as far as I'm aware of. Okay, and then the last question is, how do we incorporate surface defects, right? We know that they happen experimentally. How are we going to tackle that? Awesome question. Everything I showed you here is oversimplified in that I'm showing you perfect crystalline surfaces without defects, without segregation, without doping. We know that those are important. We know that things happen under experimental conditions. So we have to get better at making these things faster. We just had a paper out on applying deep reinforcement learning to predict segregation methods in binary alloys. That's one direction that you could go to sort of use these fast potentials to come up with creative ways to deform the surface or create defects. Shoot me an email if you're interested in that, and I'm happy to send you a link. If you had a machine learning potential that really worked for inorganic surfaces, that would also make it way easier to ask those sort of questions that you're asking. If I have to do it with DFT, where every single point takes 5 hours, it is super, super, super expensive. But if it becomes order milliseconds or seconds, I could do the same calculation with different defects and say, what is the change in activity, or what is the most stable surface? So I think the machine learning potentials are really the one of the enablers here. If we can show that this process works and it's really general, it'll really allow us to ask more interesting questions. But so far, that has been super expensive to do. Okay, and then the last question was just on email. I think Shuping is answering it, but just to throw out some of these, right? That's my email address, ulissi@andrew.cmu.edu. There's also, if you have questions about the data set or the models, there's also a discussion board at opencatalyst.project.org that you're welcome to send to. But yeah, feel free to get in touch.
So yeah, let me thank Zach again for the wonderful talk and taking so much time to answer, I would say, 80% of the questions. So if anyone has any more questions, first of all, there is on medsci.org, there is actually a forum dedicated to this particular session. So feel free to post your questions there, and someone would try to answer the questions. And of course, if you have any questions regarding Zach's work that you want to ask him personally, you can shoot him an email. Just Google Zachary Ulissi, and I'm sure you will find his email right there. Okay, so and let us once again thank our speaker, and thank you, Zach, for the time. And it has been a wonderful learning experience for me, and I'm sure for a lot of our participants as well. Thank you.
Thanks, everyone.